Hello, hello, and hello. Welcome back with me. Quite a long weekend we're in, isn't it? We just had Iladha and Hari Panchasila is coming right next after. So we got an extended week. So this week's it's gonna feel like a pretty long holiday, isn't it? But before everyone's really checks out, let's talk about some interesting things. Let's talk about Dukun. And yes, today we are going to talk about forecasting Dukun in a legal way, not working with a crystal ball, but working with numbers. So yeah, Ben Ken. Now, one of these Dukun is old school. It looks what happened last week and say next week will be exactly the same. Don't worry. While the other one is more sophisticated. It studies the trend, read the pattern, and tries to predict where things are heading. The question I set out to answer is the one you will ask to the Dukun. Every Dukun you ask. Which one is actually more accurate? Which one can predict my future? Except in our case, the crystal ball is a website traffic dataset. And instead of taking their word for it, we can measure. We can see it with numbers. Because here's the thing, when a real business predict the future, if they get it wrong, it's not only embarrassing, it's hell expensive. Digital business live and die by their ability to anticipate traffic, and the cost of getting it wrong runs in both directions. Forecasting too low and the site crashes during a traffic spike. That's a lost revenue. Damaged trust, broken SLAs. Not to the right. When the forecast is too high and you're praying for an idle infrastructure, wasted cloud spans and budget you will never get back. Accurate forecasting is what keeps you out of both ditches. Let us bring us to the central question of this study. Does a statistically sophisticated model meaningfully outperforms a really simple benchmark? So we're going to see. It's a question worth asking because in production, simple models are cheaper to maintain. It's easier to explain and it's less likely to fail. So complexity is not only worth its cost if it's delivers measurably better accuracy. That's the bar we're going to hold. To answer it, we're going to run two methods: seasonal naive and ETS, exponential smoothing, using 6 years of real website traffic. So let's start with the data. These are the daily unique visitors count from a single website spanning roughly 6 years, from early 2014 to late 2020. Over 2,000 daily observation, a rich and realistic basis for forecasting. Two things jumps out of the full series. First, a long-term upward trend. The website steadily grew its audience over time. And second is a sharp weekly rhythm. Weekday traffic consistently and dramatically outpaces the weekend, creating a sawtooth pattern that repeats every 7 days without exceptions. A slow trend and a strong weekly cycle. Those are the two features of our model have to capture. So let's prove that they are really there. Going beyond eyeballing the chart, we are going to break the series apart. The classical additive decomposition with a 7-day period, splitting it into trend, seasonal, and residual. The takeaway in the seasonal panel is the seasonal component is by far the dominant driver of the short-term variation. It dwarfs the residual noise at almost every point. To put it simply, to predict tomorrow's traffic, just knowing the day of the week gets you most of the way there. And trend panel confirms that gradual upward growth. So the structure is now clear. A powerful, stable weekly cycle sitting on a slow-moving trend. We have one more check, then we can start to draw some model. This is the statistical information. On the left, the auto correction function, how strongly each day relates with the day before it. Watch the pattern, a sharp spike, and like 7. repeating at like 14, 21, decaying really cleanly. This is the textbook signature of a weekly seasonality. Every spike is exactly 1 week apart, so the cycle is real and consistent. Not just something the eye wants to see, that's what directly justifies setting a seasonal period of 7 models. While the PSEF on the right tells the same story, with its strongest effect in the first few lags. So we've earned the headline. The weekly pattern is the dominant signal, and both methods we're about to meet are built to capture it. Now let's meet those two methods. The theme is right at the top, simplicity versus statistical adaptability. On the left, seasonal naive is the simplest possible seasonal method. Its prediction for any future day is just the value from the same weekend in the most recent week. The forecast next Monday used last Monday. The parameters, the fittings, the assumptions about how patterns evolve. That's what makes it interpretable, fast and robust, but it cannot adapt to trends or shift in levels. But on the right, we have additive exponential smoothing across all three components. It models errors, trends, seasonality at once, learning from data by weighing recent observations more heavily than the other ones. It's capable of adapting to a gradual trend that hits the catch that will met with. That same adaptability becomes a liability at a longer horizons where trend errors actually starts to compound. The clearest way to hold the contrast in our head is seasonal naive assumes that the world stays exactly as is was like last week, while the ETS assumes the world is changing and tries to stack it. So where does the tracking the change pays off, and when is assuming nothing changes is the same bet? Let's look at the forecast. This is the 7-day forecast. Notice how tightly the EDS blue line hugs the actual counts. It's reaching to recent movement in data. Seasonal naive just repeats the last weeks, so it lags whenever something shifts. At short range, that responsiveness gives EDS a clear, visible edge, nearly 40% more accurate. And I will show you what that means in a moment. It's moving on, stretching to 28 days, and watching the EDS line, that same train component starts to drift, and the error compounds across the whole month. Seasonal naive makes no trend assumption, so it has nothing to drift. You can already see it holding a steadier shape. This is where the ranking starts to flip. And the next one is when we're forecasting 90 days, the two lines almost converge. Both are just projecting the weekly shape forward, and neither can really know what happened 3 months out. So there's no clear winner to the eye, and as we'll see, the numbers start to agree. Here it's where it all comes together. The story is exactly what the chart hinted at. The best model changes with the horizon. In 7 days, the ETS win decisively. 4.07 SMAPE versus 6.72. Nearly a 40% improvement in plain terms, off by about 89 visitors a day versus 166. It's pretty huge. For planning next week's capacity, that's operationally meaningful. At 28 days, it starts to reverse. Season Life takes both MAE 254 to 269 and RMSE to 313 to 343, while ETS clings on a SMAPE by a hair. The trend that helped at a week now works against it over a month. Then at 90 days, it's a tie. MAE is 230 versus 232. Season Life has a slightly lower error MSE, meaning ETS occasionally makes a larger error, while the ETS also still having edge on the SMAPE. But averages can hide things. So before we conclude, there's one more things we are making sure the model is actually behaving honestly. Just to check, residuals are simply the error at each point actual minus the forecast. is the season life, and ES is the dash line. Red is the ETS, and the dash line is 0, the perfect prediction. The model has truly captured the structure of the data. Its residuals look like a random noise around 0. First, the good to see is that both models are broadly centered on 0. Neither is slightly biased. But now, watch how the two lines start to move together. The dips and spikes lined up almost on top of each other. Like that sharp drop near the start of July where the both crashed towards minus 900 at the same time. When both models meet in the same place, the error isn't about the model. It's genuine unpredictability in the data itself. It's like the marketing campaigns or events that simply aren't in history. There's no model could have seen this coming. And let's explain the RMS gap from a moment ago. Even with a slightly higher MAE, EDS's residuals are tighter. Its errors are more consistent in size, while season life occasionally throws a much larger miss. RMS punishes exactly those big misses. So both models are actually honest, and some of the leftover errors is just noise the model can fix, and that's the proper place we can draw a conclusion. Then let's bring it all together. The headline finding is there's no single winner. The best model is depending on how far ahead you're forecasting. For short term, EDS is the clear choice. Its ability to adapt to recent trends makes it even twice as accurate as 7 days. Different that justifies its complexity for operational planning. But beyond a week, the picture flips. Seasonal naive matches all periods 28 days on most metrics, and by 90 days, the two are statistically indistinguishable. And that's the deeper principle behind everything today. The dominant signal in this data is the weekly pattern, which both methods are capturing really well. ETS only adds value when the recent trends information gives to lift, and that lift fades as the horizon grows. That's why they converge. Far out, the ETS is just reproducing the same weekly shape seasonal naive used all along. So the recommendation is not to just pick one model. You need to be aware of the horizon or how far you are looking forward. You can deploy ETS for weekly operational planning where the accuracy turns out into cost saving, and relying on seasonal life for long-range strategic planning where its simplicity and comparable accuracy makes it the pragmatic choice. So in one sentence, use sophisticated model where the sophistication actually pays off. So yeah, you can use the simple model as well. That's it. Ciao.